Welcome to ERC TipsKnowLogy. We will just continue part 1 of 8051 Microcontroller Introduction tutorial series. In this part, we'll be talking more about the microcontroller itself. What's the difference between a microcontroller and a general purpose microprocessor? This is an Intel Core i7 microprocessor, and this is an 8089C2051 microcontroller. A general purpose microprocessors does not contain RAM, it does not have ROM, and it has no input output ports. Whereas a microcontroller has a CPU, which is the microprocessor itself, the RAM, ROM, input output ports, timer, analog to digital converter, and other peripherals. So these two are the differences between a microcontroller and a general purpose microprocessors. General purpose microprocessors we must add RAM, ROM, IO ports, and timers externally to make them functional. And this makes the system bulkier. Bulkier means bigger in size and much more expensive. These have the advantage of versatility in terms of the amount of RAM, ROM, and IO ports, which means that we can change the size of the RAM, the ROM, and the number of input-output ports. This is for microprocessors. On the other hand, for microcontrollers, it has a fixed amount of ROM and RAM and number of input-output ports, and this makes them ideal for many applications in which we are trying to save money or where the cost and the space are critical. This means that if the price is important to you, you want it to be cheaper, and you don't need to use a big space, you only have a small space, then you can use the microcontroller. In many applications, the space it takes, the power used, and the price per unit are much more critical considerations than the computing power. This is the microprocessor system compared with the microcontroller system. As you can see here, the general purpose microprocessor has the CPU on the left side, and outside the CPU are the RAM, ROM, IO port, timer, and serial COM port, which are connected through the data bus and address bus and will later on be controlled through the control bus. In the microcontroller, all of these devices are inside the microcontroller itself. So the CPU, RAM, ROM, IO, timer, and the serial COM ports are all inside the microcontroller. And in the case of a microprocessor system, these are all outside the CPU. So they are not all together in one area. Microcontrollers and embedded processors. Microcontrollers for embedded systems. An embedded product uses a microprocessor or microcontroller to do one task and one task only. Example, each one peripheral has a microcontroller inside it that performs only one task. Therefore, your keyboard will have a microcontroller, your mouse may have a microcontroller, or other devices that you are connecting to your computers might have a microcontroller inside or even a microprocessor. So as long as the microprocessor or microcontroller are inside a particular product, then it will be called embedded product. And also one of the rules is that it will only do one particular task or one specific task only. And there is only one application software that is typically burned into the read-only memory. A PC or personal computer can be used for many other numbers of applications. It has a RAM memory or random access memory and an OS or operating system that loads a variety of applications into RAM and lets the CPU run them. It contains or is connected to various embedded products. Some embedded products using microcontrollers are for home, it may be appliances, security systems, sewing machines, and even your exercise equipment. In your office, it can be your telephone or your microwave in the office or your laser printer. And for your cars, it can be your trip computer, your airbag, your security system, cellular phone, and keyless entry. These are some of the embedded products that are using microcontrollers. Now, for x86 PC embedded applications, many manufacturers of general purpose microprocessors have targeted their microprocessor for the high end of the embedded market. And there are times that a microcontroller is not enough for the tasks. When a company targets a general purpose microprocessor for the embedded market, it optimizes the processor used for embedded systems. Very often, the terms embedded processor and microcontroller are used interchangeably. So we can say embedded processor, we can also say microcontroller. They are sometimes or often used interchangeably. Now, for x86 PC embedded applications, one of the most critical needs of an embedded system is how they can decrease the power consumption and make the space smaller. In high performance embedded processors, the trend is to put more functions on the CPU chip and let the designer decide which feature or she wants to use. In many cases, the x86 PCs for the high-end embedded applications saves money and shortens development time. And we have an example here, a vast library of software where are already written, so you don't have to write the programs for it anymore. Examples Example is Windows. It is a widely used and well understood platform that we are using. When choosing a microcontroller, we have to consider so many things. But first, let's talk about the 8-bit microcontrollers. Examples of these are Motorola's 6811, Intel's 8051, which is the focus of this video tutorial. We have Zilog's Z8, Microchip's PIC or PIC. There are also 16 bits and 32 bits microcontrollers, of course, made by other chip makers. Now, what are the criteria for choosing a microcontroller? Number one, we have to meet the computing needs of the task at hand efficiently and cost effectively. We have to consider the speed, packaging, power consumption, what is the size of the RAM and ROM on the chip, how many input output pins, about the timer on the chip. Is it easy to upgrade to a higher performance or to lower the power consumption version? So these are some of the things, including the cost per unit. Another one, second, how easy it is to develop the products around it. Is the assembler available, the debugger, code efficiency compiler, emulator? We have to consider the technical support, and this follows both in-house and outside expertise. In many cases, third-party support for the chip is as good as the support from chip manufacturer. So when you say third party, this refers to the supplier other than the manufacturer. Number three, ready availability in needed quantities both now and in the future. So the leading 8-bit microcontrollers, 8051, has the largest number of diversified suppliers. And companies producing a member of 8051 family are Intel, Atmel, Philips, Cynetics, Infineon, Dallas Semi, or Maxim. Overview of 8051 family. The 8051 microcontroller was introduced by Intel and this is also known as MCS 51 in 1981. This 8051 microcontroller is an 8-bit processor, and its CPU can work on only 8 bits of data at a time. And this 8051 microcontroller has 128 bytes of RAM, 4 kilobytes of on-chip ROM, 2 timers, 1 serial port, 4 input-output ports, each 8 bits wide. So if you multiply 4 input-output ports with 8 bits wide, it will be 32 input-output pins. We also have 6 interrupt sources. And the 8051 became popular widely after allowing other manufacturers to make and market other models of the 8051, but all of them remains code compatible. This is the 8051 microcontroller block diagram. At the top, we have the external interrupts going on the interrupt control box. We have the on-chip ROM for code. We have the on-chip RAM, timer 0, timer 1, and the counter inputs going to the timers. We have the CPU, oscillator, bus control, input-output ports, serial port. The input-output ports consist of the P0, P1, P2, and P3, where P0 and P1 are used for address or data. Actually, it's P0 and P2. P0 and P2 are used for addresses, and P0 can be used for address or data. And we have the serial port that has transmit and received signals. This is the oscillator, and usually we are using 11.0592 megahertz with 230 picofarad capacitors here connected to the ground. So this is the 8051 microcontroller block diagram. Now, looking at the 8051 pin diagram, you will see that the 8051 has 40 pins. Pin number 1 to pin number 8 refers to the port 1 from P1.0, which means port 1 bit 0, or you can also say port 1 pin 0, up to port 1 bit 7 or port 1 pin 7. On number 9 is the reset. On number 10, we have P3.0 up to 17, which is up to P3.7. So port 3 bit 0 up to port 3 bit 7 starts from pin number 10 up to pin number 17. Port 3 has another function. So aside from being input-output port, it can also be having a third function, or this is like the transmit, transmit, interrupt 0, interrupt 1, timer 0, timer 1, write, and read. For number 18 and 19, this refers to extal 2 and extal 1 respectively. And of course, we have the ground on number 20. On number 21 up to 26, up to 28 rather. So from 21 to 28, we have port number 2.0 up to port 2.7. But port 2.0 has another function. So aside from this, port number 2 is also an input-output port, but it can also be used as an address. So in other words, these ports have three functions: input, output, and address. From address 8, A8 up to A15. This port number 2 works together with port number 0 to provide a 16 bits address. That's why this is A8 up to A15, because A0 starts from 39 up to A7. So 39 down to 32, that's where we will get A0 up to A7, followed by A8 from port 2.0 up to port 2.7, A15. In other words, from A0 to A15, that's 16 bits address. Now moving on number 29, we have PSEN. Number 30, we have ALE. Number 31, we have EA. And then from number 32 up to 39, we have ports P0.7 down to port P0.0. And this port 0 has another function aside from input output ports. It can be used for address and it can also be used for data. That's why we can use this for D0 up to D7 and also A0 up to A7 aside from input or output. And lastly, we have the VCC, which is the power supply of positive 5 volts. So again, port 1 has 8 pins, 1 to 7, used only as input or output pins, P1.0 to P1.7, with no other third function. The reset, RST, terminates all activities, and the P0 to P3, actually P0 to P3 becomes input ports. So we have to correct that one. It should be P3, not P4. So P0 to P3 becomes input ports upon reset. So when you reset it, and the pointer must be pointing on reset here, RST. So let's do that. Let's just correct this one for a while. So the reset or RST, when you reset it, the port 0 to port P3 will become input ports. Now port 3 has 8 pins from 10 to 17, and these are used as input or output pins, P3.0 to P3.7. Also most commonly used to provide the important signals that I have mentioned before from RxD to RD. So the P3 has input function, output function, and a third function here, special functions here. Now, on the other hand, the Xtal2 and Xtal1, number 18 and 19, a quartz crystal oscillator will be connected between the Xtal2 and Xtal1. And then there will be two capacitors connected to it also of 30 picofarad. And each are connected on the Xtal2 and Xtal1 and then grounded. Now, if the frequency oscillator like the transistor to transistor logic oscillator is used, it will be connected only to Xtal1 and Xtal2 will be left unconnected. Maybe later on you will be seeing it on the next slides. Now for port 2, as I have said, this has 8 pins, 21 to 28, and this is used as input or output pins, P0 0.0 to P0.7. So this is wrong. It should be P2.0 up to P2.7. So we might as well correct it now. So it should be P2.0 and the other one is P2.7. So the port 2 has P2.0 up to P2.7. Okay, so when connected to an external memory, the P0 provides the upper 8 bits of the 16-bit address A8 to A15 and cannot be used as input-output. Now, the EA stands for external access. This is an input pin, and this is connected either to VCC or ground, and this cannot be left unconnected. PSEN stands for Program Storage Enable. This is an output pin, and in 8031, this is connected to the OE pin of the ROM. And ALE means Address Latch Enable. This is an output pin, and the active high, and it demultiplex address and data connected to G pin of 74LS373. Now, port 0, on the other hand, has 8 pins again from 32 up to 39, and this is used as input or output pins from P0.0 to P0.7. When connected to an external memory, P0 can provide both address and data, AD0 to AD7, and it provides lower 8 bits address also of A0 to A7 in combination with P2, which refers to input output port, but it can be used as A8 to A15. So as I have said, we can provide 16 bits address from A0 to A15 using port 0 and port 2. And lastly, we have the voltage source VCC of positive 5 volts. Here you go. This is the 8051 pin diagram. Now, just to be clear, the reset pin is an input and is active high or normally low. And upon applying a high pulse to this pin, the microcontroller will reset and stop all activities. And we also call it as power on reset. And this will activate a power on reset that will cause all values in the registers to be erased or lost. And example, in this table, you will see the registers and its reset values. Upon having a power on reset, or if the reset pin a high pulse is entered to this reset option or choice. So the reset value of some 8051 registers are here, and you can see that the program counter becomes 0000, for example, and we have here the ports P0 to P3 will become FF or 1111 1111. Now, the 8051 has an on-chip oscillator but requires an external clock to run it. And as you can see here, Xtal2 and Xtal1 has a uh, oscillator here, a quartz crystal oscillator. And we also need two capacitors here, 30 picofarad connected in series, parallel. The series of the two capacitors is parallel to the crystal oscillator, and then all of them are connected to the ground. This is one way to connect the Xtal2 and Xtal1 using a quartz crystal oscillator. Now, if you use a frequency source other than a crystal oscillator, like for example, you use a transistor to transistor logic oscillator, then you will have no connection on Xtal2, and there will just be a Xtal1 external oscillator signal connected to Xtal1 and then the ground. In order for the reset input to be effective, one condition is that it must have a minimum duration of two machine cycles. So in other words, the high pulse must be high for a minimum of 2 machine cycles before it is allowed to go low. And this is the picture or figure of how you will connect the Xtal2 and Xtal1. And as you can see here, the pin number 18 and 19, as I have mentioned before, is connected to a specific crystal quartz oscillator. And here, we're using 11.0592 megahertz oscillator. And we have here the 30 picofarad capacitors. And in this way of power on reset circuit, we will be having a VCC connected to a 10 microfarad capacitor in series to an 8.2 kilo ohms resistor directly connected to the ground. And compared with, of course, we have here another way. If you use a push button switch, we have here a power on reset with the bounce. You will just have a parallel switch to the 10 microfarad capacitor. But basically, these two circuits are the same except that the 10 microfarad here has no parallel switch. Here, there's a switch that you can push in order to reset. Now, for the port 3, we have to take into consideration that it has other special functions that are related to serial communications in the case of pin 10 and 11 or P3.0, P3.1. And the function of this is for receive and transmit signals. And for pin 12 and 13, this will be for the external interrupt 0 and interrupt 1. And we also have the timers T0, T1, and the read or write signals from the external memories or of external memories are on pin 16 and 17. So in systems based on 8751, 89C51, or DS89C4X0, the pin number 3.6 and 3.7 are used for input-output, while the rest of the pins in port 3 are normally used in the alternate function role. That's it for the second part of our 8051 microcontroller tutorial series. Thank you. Please subscribe, like, and share our video for our road to 1,000 subscribers. Thank you.